Okay. Today is a review session for exam 2. About exam 2, the time is this Thursday from 11 to 12:15. The location is 105 in the classroom building. The sections covered by this exam, 4 sections, 1.7, 2.1, 2.2, and 2.3. Just like exam 1, you can have a formula sheet, one formula sheet, A4 size. By A4 size, I mean about 8 inches by 11 inches. You can write any feeds on the both sides of the formula sheet. And also you can have a basic calculator. How to prepare for the exam? I suggest review your homework assignments. You can find my solutions on wild courses, and pick some examples in the book to read, and also try some problems in the exercise sections in the book. Yeah, this is my suggestion for preparing for the exam. Okay. Now, take a review section by section. Section 1.7. What is 1.7 about? Section 1.7. It is about linear dependence and independence. To study mathematics. Mathematics is a subject of definitions and theorems. So, definitions. Okay, number 1. If a vector is a linear combination of some other vectors, say v1, v2, vk, a linear combination, that means that we can find some scalars c1 times v1, c2 times v2. A combination of these k vectors in this form is a linear combination. If V is a linear combination of these k vectors, we say that vector V linearly depends on these k vectors. Otherwise, if we cannot write V as a linear combination of these k vectors, we say that V linearly depends on the k vectors. Yeah, linear dependence and independence. Second definition: a set of k vectors is said to be a linearly dependent set. Dependent set. What it means? If the following vector equation, say x times v1, x2 v2, xk vk is 0 if this vector equation has non-trivial solution. Non-trivial solution. This vector equation, because the right side is 0, this equation always has at least one solution. Say 0, 0, 0, 0 is a solution, but we call the solution trivial solution. If this vector equation has non-zero solution, then we say that the set is a dependent set. Otherwise, independent set. Otherwise, independent set. If this vector equation has just 0 solution, then the set is independent set. Definition number 3. We say that k vectors are linearly dependent. We mean the set of these k vectors is a linearly dependent set. Similarly, we say that these k vectors are linearly independent. What it means? The corresponding set is a linearly independent set. Okay, yeah, definition. Okay, then definition. Next, theorem. Okay, mathematics, definitions, theorems. A theorem. How many theorems in this section? But anyway, theorem number 1. Theorem number 1. Okay. Let S be a set of k vectors. Okay. Then A. S is a linearly dependent set. That means that this vector equation has non-zero solution. If and only if at least one vector in S is linearly dependent on other vectors in S. Here, I only say that at least one. I don't say that any vector in S linearly dependent on the other vectors. I don't say that. Okay. Yeah. B. S is a linearly independent set if and only if row vector in S is linearly dependent on other vectors in S. Okay. When a set is a linearly independent set, the vectors in the set are independent to each other. Okay, to each other. Yeah. Okay. Now, definitions, theorems, then examples. Yeah. Example 1. We have some vectors, 4 vectors. 1, 2, -4. V2, 4, -A, 16. V3, V4. Two questions. Question A, determine if the set of these 4 vectors is linearly independent. Let me answer this question first. How to answer this question? Go back to the definition. Solve this vector equation. X3, V3, V4. Solve this vector equation. If the vector equation has non-zero solution, then this set is dependent set, not independent. Now, let me solve it. This vector equation, X4, is a linear system. Augmented matrix of this linear system is augmented matrix. A, right-hand side is 0, right? A, first column is V1, second column V2, V3, V4. Right-hand side is 0. Solve this linear system. Okay, let me put V1. V2. V3. V4. Then right-hand side. Solve this linear system to see whether or not the linear system has non-zero solution. Okay, now let me solve it. Perform eliminations. Transform the matrix into epsilon form. This linear system must have at least one solution because the bottom non-zero row, this row, the bottom non-zero row is not in this form. It's not in this form. So this linear system, at least one solution has. Okay. Then how many solutions? Look at if the linear system has 3 variables. First column, pick a column. So x1, first column corresponds to x1. x1 is basic. Second column, low pivot entry. So second column is a free column. So x2 is free. A linear system has solution and also has a free variable. The linear system has infinite many solutions. So the linear system, because the system has free variables, the linear system has non-zero solution, non-trivial solution. Non-trivial solution. Therefore, this vector equation has non-trivial solution. By definition, the set is a dependent set, not independent. So conclusion is this set is a dependent set, linearly dependent set, not independent. This is a solution to part A. Now part B. If dependent, yes, part A says that the set is dependent. Then find a linear dependence relation among these 4 vectors, among the vectors. Now this time, to answer B, you need to solve the linear system for one non-zero solution. Okay, now this is the epsilon form, reduced epsilon form. Okay, I write the epsilon form in equations. Yeah, write this reduced epsilon form in equations. First row is x1 plus 4x2 minus 3x3 is 0. Second row is x4 is 0. The last row, 0 is 0. Yeah. Solve this linear system for basic variables in terms of free variables. The first equation, x1 is basic, x2, x3, free. Move them to the right side. Okay. Second equation, x4 is 0. And x2, x3, arbitrary. Yeah. This is the general solution of this linear system. General solution means all the solutions. Okay, now let me pick one solution. Let me set one non-zero solution. Say, let me set this guy to be 1 and this to be 0. One solution is x1, x2, x3, x4. Let me see. X2 is 1, x3 is 0, then x1 is negative 4. X2 1, x3 0. And x4 always 0, always 0, 0. After we have a non-zero solution, then one dependent relation among the 4 vectors is, okay, plug in the solution in this vector equation. Then we have 4, negative 4, V1 plus 1 times V2, and then plus 0 V3 plus 0 V4. It is 0. Yeah. This is a one relation. From this relation, we can see that V2 depends on the other vectors. How? I keep V2 on the left side and move all the other vectors to the right side. See, V2 is a linear combination of other vectors. So V2 linearly depends on the other vectors. When a set is a linearly dependent set, at least one vector in the set depends on the other vectors. Say V2 depends on the other vectors. And also V1 depends on the other vectors. If you keep V1 on the left side, move all the vectors to the right side, then you will see V1 depends on the other vectors. This is example 1. Example 1. Now example 2. Example 2. If a set V1, V2, VK, let me give a name to this set. Say, let me call it S. Contains the 0 vector. Then the set S is linearly dependent. To answer this question, at least 2 solutions. Solution 1, by definition, we need to solve this vector equation. Vector equation. K vectors, sorry, K vectors. K vectors. Say xk minus 1, vk minus 1, xk, vk. Solve this vector equation to see whether or not the vector equation has non-zero solution. The problem says one of the K vectors is a 0 vector. For example, how about let me assume this guy is 0 vector. Then I can find one non-zero solution, non-trivial solution is x1 is 0. 0 times v1, 0. x2, 0. And so on. xk minus 1, 0. Non-zero solution. But I can let xk to be 1. Yeah, this is a solution to this vector equation, and the solution non-trivial. Therefore, by definition, the set is linearly dependent set. So S is dependent, a dependent set. This is solution 1. Solution 2, I can use the theorem here. The theorem here. S is a linearly dependent set. If one vector depends on the other vectors, then the set is a linearly dependent set. Let me use this theorem to answer the question. Again, let me assume Vk is 0. Then I can write Vk as a linear combination of the other vectors. How? 0 is 0 scalar times V1 plus 0 times V2 plus 0 times Vk minus 1. So Vk is linearly dependent on V1, V2, Vk minus 1. Therefore, by theorem, S is a linearly dependent set. So there are 2 solutions to this example. Done. Example number 4. Example number 3. Okay. Then V1 be 1, negative 3, 2. V2 be V3 H. Okay. H, I don't know H, will be determined. Now, 3 questions. First one, for what values of H is V3 in the set spanned by V1 and V2. Now you need to recall the meaning of this notation. This notation means the set of all possible linear combinations of V1 and V2. So this question actually is for what values of H, V3 is a linear combination of V1 and V2. So to answer this question, we need to solve this equation. V3 is X1 unknown times V1, X2, V2. If this equation has solution, then V3 is a linear combination of V1 and V2, and therefore is in the span by these 2 vectors. Right. Now, how to solve this equation? It is a linear system. Augmented matrix is augmented matrix. Coefficient matrix, X, X1, X2, unknowns. Coefficients of X1 is V1. Coefficient of X2, V2. And then equal to left hand side V3. Solve this equation. Okay, in detail, it is 1 negative V2. This is a V1, V2. And then V3. Okay, now let me solve this linear system to see if I can find a solution. Okay. Okay. Forward elimination to reduce this to epsilon form. Yeah. 1 negative 3 5 0 0 1. Not in epsilon form yet. H is a number. I just don't know what the number is. It is a number. So I can use this number to eliminate the number H minus 10. How? I multiply negative H minus 10 to row 2 and then add to row 3. Yeah. Row 3 to make this matrix into epsilon form. Zero, zero, zero. Now look at the bottom non-zero row. Yeah, this row. This row, actually, it is an equation. 0 times x1 plus 0 times x2 is equal to 1. No matter what x1, x2 are, this equation is never true. So therefore, for any h, the linear system or this vector equation has no solution. So therefore, the conclusion is V3 not in the span by V1 and V2 for any h. This is a part A. Now, second question, B. For what values of h is the set of the free vectors linearly dependent? To answer this question, refer to the definition. A set is a linearly dependent set. What that means? Go back to the definition. To answer this question, we need to solve this vector equation. This is the definition. If the vector equation has non-trivial solution, then the set is linearly dependent. Okay, now let me solve. Augmented matrix. Coefficient matrix together with y side. Coefficient matrix, first column is the coefficient of the unknown x1, so v1. Second column, coefficient of the unknown x2, v2, and then v3, together with right side. So in detail, plug in v1. 1, 3, 2, 3, 9, 6, 5, 7, 8. Then right side right side. How to solve this linear system? Reduce it to epsilon form. Epsilon form. Uh, 1, 3, 5, 0, 0, 0, 1, 0, 0, 0, h minus 10, 0. This matrix is not in epsilon form yet. Again, I use this number to eliminate this number. Negative h minus 10 times rho 2 add to rho 3. Then I get epsilon form. About this linear system, the bottom non-zero row is this row. But this row is not in this form, not in this form. Not in this form. If a row is in this form, no solution, but not in this form. So this linear system has a solution. Actually, the second row is this equation. 1 times x3 is 0. So there is a solution. The solution is x3 is 0. So second row has a solution. Okay. The linear system has solution. Now next, ask yourself, how many solutions? I can see first column, pivot column, second column, free column. So x2 is free. The linear system has infinitely many solutions. Of course, there are non-trivial solutions. So the conclusion is conclusion. The linear system has solution and has infinitely many solutions. Conclusion is the given set linearly dependent. The given set is linearly dependent. Actually, no matter what h is for any h. For any h, the set is linearly dependent. Yeah, this is a example number 3. Now let me pick these examples are from my notes. Let me pick some problems from the exercise section. Say example number 4. This is a problem number 33 in the book, section 1.7. Okay, now let me see. 1.7. Problem number 33. Okay, now the problem is how many pivot columns must a 7x5 matrix have if its columns, each column is a vector, are linearly independent. And why? Explain. Okay. All right. How about let me give a name to this matrix. Let me name it A. Okay, A. A is 7 by 5. Let me cut the matrix A in columns. A1, A2, A3, A4, 5 columns, A5. Each column has 7 entries. Now we assume the columns are linearly independent. Okay. That means that by definition, linearly independent. That means that this vector equation A5 has only trivial solution. Only trivial solution. Okay. Actually, this vector equation is AX is equal to 0, right? The left side is A times X. X is this vector is the unknown vector. So this vector equation has only trivial solution. That means that this linear system has only trivial solution. This linear system has only trivial solution. That means that no free variable. If the linear system has one free variable, the linear system has non-trivial solution. So no free variable. That means that all columns in A are pivot columns, right? All the columns in the coefficient matrix are pivot columns, no free variable. So how many pivot columns? 5 pivot columns, because of A has 5 columns. So A has 5 pivot columns. Done. This is section 1.7. Then section 2.1. What 2.1 is about? Matrix operations. How many matrix operations? Summation. We can add two matrices of the same size. A plus B, same size. If the matrices are different size, not computable. Summation, subtraction, multiplication, but no division. Okay, in matrix operations, no division. The difficult one is multiplication. Okay, let me present the formulas to compute A times B. Okay, yeah. Let A be M by N, M by P, M by P, B be P by N. Pay attention. The number of columns of A should match the number of the rows of matrix B. Otherwise, A times B, not defined or not computable. Then A times B is M by N. Cancel the middle P. Okay. The formula, two formulas. Formula number one. So write down the formulas on your formula sheet. Okay. A times B. How to compute A times B? Cut matrix B in columns. First column, second column. How many columns? N columns. Then distribute A to each column. Then it is A times B1, A times B2, and A times Bn. I remember we have a homework problem about how to use this formula to compute A times B. Review your homework, okay? Formula one, second formula. Formula number two, A times B. It is a matrix. The ij entry of this matrix is row I of A times column J of B times what is row I of matrix A? The entries are AI1, the first entry, row I. AI2, because A is M by P. The last entry in row I is AIP. Then times column J. Column J, B1J, first entry, B2J. How many entries in column J? B is P by N, so PJ. So the numbers in row I and the numbers in column J are equal. Then computable. Otherwise, not computable. Okay, now row I times row J. That means that AI1 B1J times plus AI2 B2J times, and so AIP BPJ. Yeah. Formula two. Yes. Some question. I don't know, is the Zoom okay? Yeah. So maybe your problem, your old problem, is it as some other people says that the Zoom works well. Okay. This is two formulas. So write down your formulas in on your formula sheet. Let me take some examples. Okay. Example one. Let V be a vector. A vector is a matrix. V, a second vector. A, B, C, second vector. Now, find U transpose times V. and U times V transpose solution. Yeah. By this example, take a review about what is transpose. Transpose a matrix. How to take transpose on the matrix? Draw the main diagonal line, then rotate the matrix about the diagonal line. Then to get the transpose. Okay, now U transpose. Draw the main diagonal line, then rotate U about the line. Then we get -2, 3, 4. 1/3 matrix. Now times 3. A, B, C. This is a 1/3. 3/1. Cancel the middle 3. So the answer is 1/1. 1/1 matrix. 1/1 matrix by row column formula, by formula number 2. The entry is -2 times A plus 3 times B. -4 times C. Yeah. They say 1/1 matrix. U times V transpose. U V transpose A, B, C. Now this time, the first matrix is 3/1. Second matrix 1/3. The result is 3/3. Cancel the middle 1. So it is a 3/3 matrix. The 1/1 entry is row 1 times column 1. So -2A. 1/2 entry, row 1 times column 2, -2B and -2C. Similarly, 2/1 entry, row 1 times column 1. Yeah. Yeah. So this vector times transpose of V is a 3/3 matrix. This matrix. Yeah. Let me see. Let me pick example from the book, section 2.1. Uh, 15. Problem 15. Yeah. Example number 2. Problem 15 in this section 2.1. Yeah. It is a true false problem. If A and B are 2/2, then A times B is column 1, the first column of A, times the first column of B. Column 2 of A times column 2 of B. True or false? True or false? Clearly, this equation is false. Why? By formula solution. A times B. It is the whole matrix A times first column of B. Not just the first column of A times the first column of B. The whole matrix A times the first column of B. the whole matrix of A times the second column of B. This is the correct formula, and this formula is wrong. So false, false. How about 16? Problem 16, also a true, false problem. Okay. If A and B are 3 by 3, then A times B is equal to A times the first column of B plus A times the second column of B plus A times the third column of B. True or false? The answer is false. Why? A 3 by 3, B 3 by 3. A times B should be 3 by 3. Now, look at this sum. A 3 by 3. First column of matrix B is 3 by 1. So A times B is 3 by 1, a vector. And also this is a vector, a vector. Vector plus vector plus vector, it is a vector. So actually this sum is 3 by 1 vector, not equal. The correct formula is A times B is a matrix 3 by 3. First column A times B1, comma, not sum, okay? A times B2, comma, not sum, A times B3. This is the correct formula. 3 by 3 matrix, not 3 by 1. Okay. So this is a false, false. Section 2.1, 2.2. What section 2.2 is about? The inverse of a matrix. Again, mathematics, let me emphasize again, mathematics is a subject of definitions and theorems. First, definition. What is the meaning of the inverse of a matrix? Okay. Let A be a square, okay, not rectangular matrix. Say the size is n by n. If you can find other matrix, another matrix C, same size, C is Z the inverse of A if the following two equations, A times C is identity matrix. In matrix operations, identity matrix plays the role as the number 1 in real number operations. A times C is 1, and C times A is 1. About these two equations, you only check one equation. The other equation automatically true. If one is true, the other is true. Okay, this has been proved theoretically. Okay. So you just need to make sure one of these two equations is true. Then C is inverse. Okay. The notation for C is this notation, okay. Inverse. Definition. Then theorems. Two theorems. Maybe write down these two theorems on your formula sheet. For 2 by 2 matrix, it is easy to know whether it is invertible if determinant 2 by 2 matrix A times B minus C times B non-zero. A is invertible, and invertible A has inverse, and the inverse is equal to 1 over determinant times D B C A. On the other hand, if determinant 0, A has no inverse. Theorem 1. Now the second theorem in this section is theorem number 2. For a general n by n matrix A, how to know the matrix has inverse? Some people may say that compute its determinant, but determinant is chapter 3, not now. Okay. Then for n by n matrix, how to know the matrix is invertible? Yeah. A is invertible, has inverse, if and only if A can be reduced to identity matrix. Yeah. Two theorems. Okay, now the next question is how to compute A inverse. How to compute A inverse? Solve this equation. X is a matrix, identity matrix. Solve this equation. If the equation has solution invertible, the solution is inverse. Okay. Then how to solve this equation? Step 1. Form augmented matrix. Right. Coefficient matrix together with right hand side. Okay. Then reduce augmented matrix to a matrix of this form. If successful, may not successful. If successful, then C is A inverse, because this augmented matrix actually is this equation. Yeah. So this is X. Yeah. The solution is C. So C is A inverse. If not successful, then A has no inverse. Why? By this theorem. By this theorem. A cannot be reduced to I, so A has no inverse. So, yeah. Okay. Some properties, some basic properties about inverse. Okay. Some basic properties. A inverse, then inverse again is matrix A. B, A times B inverse. Pay attention. It is not A inverse times B inverse, but B inverse times A inverse. Okay. Remember this. Okay. C. A take transpose, then take inverse is equal to take inverse first, then take transpose. Okay, now let me take one problem to present 2.2. Okay. This is a problem number 29. Solve this equation. For x, okay, solution. Hey, remember, matrix times matrix is not commutable. That means that not equal in general, usually. Okay. Okay, now how to find x? I move C inverse to the right side. How? Multiply the equation from the left side, don't from the right side. From left side, okay. Then C inverse cancel. C times 1 is C, okay. Then next, move B inverse to the right side. How? Multiply the equation from the right hand side by B, okay. From the right side by B. C times B, not B times C. C times B, not equal to B times C, okay. Then cancel. Final step, move A to the right side. How to move A to the right side? Add negative A to the both sides. Done. This is the solution. Okay. How about 43? What 43 is? Oh, 43. 43 just compare the inverse of a matrix. So you can now take a look, review your homework. Okay. Okay, now section 2.3. This section only one theorem. Write down the theorem on your formula sheet. Only one theorem. Invertible matrix theorem. Only one theorem. Okay. The theorem is theorem number 8 in the book on page 145. Yeah. So this theorem makes a list of properties about invertible matrix. Yeah. So it is a long list. Let me present. Let me pick problem number 26 in section 2.3. Yeah, in section 2.3. Let me see. Problem 26. All right. If C is 6 by 6 and the equation is consistent for every vector V. The vector, of course, are in R6. Now the question is it possible that for some V, the equation has more than one solution? The answer is no, not possible. Why? Because Cx times V is consistent. A linear system is consistent, means the linear system has solution. Okay. For all V, by this theorem, C is invertible. So when C is invertible, this linear system has only one solution. Why? Because I can move C to the y side. Multiply the equation from the left side by C inverse. Yeah, just one solution. Okay, no more than one solution. Only one solution. Yeah, only one solution. Only one solution. Yeah, this is 26. Now 29. Very similar. Problem 29. If the equation has more than one solution for some y, can the columns of G span the whole space? Okay. If a linear system has more than one solution for some y, then G is not invertible. Why? Because if G is invertible for any y, the linear system has only one solution. So G is not invertible. So therefore, by this theorem, the columns of G cannot span the whole space. Done. So section 2.3, only one theorem. Yeah, let me stop here.